are back, and this time we are going to model the Mitsubishi VRF system. So first thing we will do is save this as a new file. We'll just use this right here, save, yes. The next thing that we need to do is download the Mitsubishi library off of the building component library. So we can go in here and just search for Mitsubishi. It's going to be this one right here. Click download. And it's going to be this zip file that we downloaded. Open it up. There is an XML file in here. This is basically this description plus some additional categorizing information that the building component library uses to categorize measures and components. We'll open up the files folder, and there's going to be a couple of files in here. There's an OSM file, and then there's a PDF. What we can do is just copy these and put them into our project folder. And then so this is an OSM file, and what we can do is we can reference this file in our project. So let's go back to our project and go to Preferences, and let's change default libraries, and we'll just add this default library in here, which is going to be this OSM file that we just downloaded. Click OK. Let's see. The next step would be, I guess we can just delete this old VRF system. This is the generic system that we modeled the last episode. So click out of here and just delete this. The next step is to go to the Library tab on the right and scroll down to VRF System. And we are going to be looking for this one right here, which is a PUHY EP72. And it's going to give us some options for ducted and non-ducted. Yeah, let's step back a little bit. We can open up the notes to the energy modeler. That was the PDF file that came with the library. So we can open this up here, and these are all of the Mitsubishi objects that have been modeled so far. It's going to be this one here, and we'll just take a look at this. So these are all the notes to the energy modeler as far as customizing the object for your purposes. And so there's certain performances that are not included in the model, but you know, it's just depends on what you're modeling. So the first thing to look at is the naming scheme. So there's two different options with Mitsubishi, ducted and non-ducted for performance, efficiency performance, and that's going to be these values here. This is not a very good PDF, but we can take a look at this. So yeah, the first number is going to be the ducted number, and then the second number is the non-ducted number. And that's what these are. It's the naming convention is non-ducted, ducted, and then there's Mitsubishi also has a standard and a high heat switch setting. So these are the naming conventions that we'll be using. I think what we can do just for simplification is just go with the non-ducted. The model that we have is very simple, and you could go through the proportional calculation similar to the way we did it last time with the generic VRF system. And so if you have a proportion of indoor units that are ducted versus indoor units that are non-ducted, the performance, the coefficients of performance might land somewhere in between there. But for this example, let's just go with non-ducted equipment. With that said, so we're going to do non-ducted, and we will use the high heat option because of the climate that we are modeling in. So let's choose non-ducted high heat EP72. And open this up here. And then the other equipment that we needed to model was a PEFY P30. And so those are going to be under the terminal units, PEFY P30. It's going to be this here. And the other one was the PKFY P30. PKFY P30 right here. Again, we drop in our thermal zones, and we need to assign the master thermostat, similar to last time. This apparently we needed always availability schedule. We'll select always on discrete. And then we also need to assign the thermostat locations for these. And that's it. We can go back to our thermal zones, and you'll see that the terminal units have been assigned to the thermal zones. So let's go ahead and run the simulation. So the simulation has completed successfully. Let's take a look at the error output file. We have a number of warnings here. So here, this is just giving a warning. Fan system model has a discrete number of speeds. I'm not even sure why this isn't a warning. Maybe it should just be more of a informational thing. This one also has some discrete speeds. rated air. So this is a rated air volume for flow rate per watt of rated total cooling capacity is out of range. And this is a common warning with EnergyPlus for these variable refrigerant flow cooling and heating coils. EnergyPlus does a reality check and says, is this airflow per capacity realistic? And the lower bound is this number, and the upper bound is this number, and it says that our equipment sort of fell outside that, so it's actually a little bit more efficient than, or it's got a higher flow per capacity than what EnergyPlus was expecting, which means higher air changes and possibly a little bit warmer temperatures in cooling. But there is, we can take a look at the notes to the energy modeler on this, and we can just look at, let's see, this was the PEFY. So if we look at the PEFY, you'll see that there are some notes here talking about this, and basically the gist of it is that this is just a guideline, and the AHRI test standards do not have any limitations on this. So it's just a warning, and it's not that important. Moving on. Let's see, this is talking about how the VRF heat pump operating temperature in heating mode limits have been exceeded and VRF system is disabled. And it's saying that the outdoor temperature was almost 25 degrees, which is quite warm. Which seems strange why the heat pump would be heating with that high of a temperature. But if you go on to notice, this was caused during the warm-up period. So this was actually before the computation had completed convergence, and it was trying to size the system. So this is actually not that important, and we'll see that a little bit later here. Let's see. And then this is the same air volume flow rate per watt of capacity. Note, again, that's not important. That's just a guideline. And then again, we also get the same error here. So when it's really cold outside, it says that, let's see, for some reason it's trying to cool when it's really cold outside. But again, this is during warm up, so we're not worried about that. And for your information, warm up is just when it's doing equipment and zone sizing. It's not actually doing the run of the model for the calendar year. And then finally, let's see, we have this one is throwing a terminal unit part load ratio calculation failed, PLR limits of 0 to 1 exceeded. And I do not know why it's causing this problem. It says fill out a bug report, which I have done. And I'm not sure why that would be a problem, because these terminal units could conceivably exceed a part load ratio of 1. Moving on, let's see. Again, this is when it's exceeding the maximum heating temperature, and it says it's occurred during the warm-up. And it actually doesn't occur during the sizing. So there we are. And that's all. So it looks like our simulation was successful. And so let's go ahead and open it up and take a look at the report. So this is the Mitsubishi report. And then let's also open up the generic report as well and do a comparison. So here is our generic one, the one we just did in the previous example. And it looks like we have about 125,000 BTUs a year. And the Mitsubishi is like 118,000 BTUs. So a little bit better. We were actually pretty close. We did a good job guessing with the generic one. Let's see. Another thing we could look at is the unmet hours for the equipment. And so for the generic, we have for heating, we have about 575. Cooling's virtually nothing. And then for the unmet hours for the Mitsubishi, this one's actually quite a bit higher. Virtually 0 for cooling, but this is higher for heating. But actually, this is if we're talking about talking about occupant weighted degree hours. Realistically, we probably should be just looking at unmet degree hours, which is 575 versus 568. So they're very close. I suspect the occupant weighted hours are higher for the Mitsubishi, because that takes into account some other factors, such as occupant comfort, and it gets multiplied by, I believe it gets multiplied by the number of occupants in the room. And so it could be because of our higher airflows. I'm not really sure. At any rate, the unmet hours look very similar, except for those occupant weighted hours. So might be something to look into further. Let's see. So let's take a look at the notes to the energy modeler. So again, let's see. I noted that these are notes that the energy modeler might use to adjust their model. So like for this PEFY equipment, you can see this is a ducted unit. So right off the bat, you're going to have to make sure that the static pressure of the unit is what you were expecting to be. And let's see. and then you can take a look at the static pressures that it's capable of and make those adjustments in your model. So to do that, you could go to the VRF and just select this and edit the fan design pressure rise. So right now it's at 0.8 inches of static. And keep in mind this is total static pressure. So this is internal and external pressure that's on the system fan. So those are the notes for the terminal units. We can take a look at the notes for the outdoor unit. There's more of these. We already kind of discussed the naming convention. There's this one here. So if the outdoor unit will be installed below the indoor units, you would have to adjust these minimum and maximum outdoor temperatures in cooling mode on the outdoor unit. So let's select this, and that would be these values right here that would have to be edited. We can change these to metric units. So yeah, -5 to 52. We would have to change these to 0. Let's see. Cooling mode, 0 to 43. So yeah, let's see. We discussed high heat. Cooling part load fraction correlation curve. So there are a number of curves that Mitsubishi does not provide any information for. So in those cases, the EnergyPlus default curve was used. And apparently the EnergyPlus curve is just an output of 1. So it doesn't actually account for any inefficiencies below minimum part load ratio. So that would be compressor cycling on and off. But that should be fairly minimal as long as you select the proper sized equipment. This model does not have waste heat recovery. You would have to adjust your equivalent piping length based on your project. Vertical height used for piping correction factor. This one default is 10, but it's actually not used. Mitsubishi didn't have any published D rates for that. And the EnergyPlus default is essentially 0. Crankcase heater power per compressor. So Mitsubishi does not have any crankcase heaters, so that's not actually used. Mitsubishi does have a drain pan heater, but EnergyPlus doesn't have any ability to model that. Defrost energy input modifier. So these are just more informational things. Condenser inlet node. So this would be, you might want to change the condenser inlet load if the equipment's going to be installed in some odd location, like way up high on a high-rise building, where the temperature it's going to be different from ambient, or if it's going to be installed in, I don't know, an alleyway or maybe some machine room or something. And then this one has no heat recovery for this model. So those are just some notes for the energy modeler to keep in mind. And then it goes on to discuss to show what the curves are. So we can see that. So for cooling capacity modifier curve, The Mitsubishi equipment actually has higher capacity in the lower temperatures, but then it drops down quite a bit at higher temperatures, whereas the default EnergyPlus curve actually has this kind of a little bit better capacity at those higher temperatures. Yeah, let's see. And this is actually for 15 degrees wet bulb, so we should probably be looking at indoor temperatures more like this. So you can see here the EnergyPlus curve is actually quite a bit better than the Mitsubishi. So you might be kind of skeptical about that. Again, let's see, for the energy input modifier curve, again, it looks like Mitsubishi is actually better than the generic is better than Mitsubishi. So I would be fairly skeptical about that, since these generic curves were put together almost a decade ago. So, and then cooling energy input modifier function of part load ratio. These curves are similar. Looks like the Mitsubishi actually performs better than the EnergyPlus generic curve, until it gets above part load ratio of 1. So anyway, and then it goes into some piping correction factors, and then also the heating performance. So some interesting curves to look at. So that is how you model Mitsubishi equipment in OpenStudio. So the final task that we have is to take a look at a couple of other VRF systems. Namely, we are looking at a Daikin system and an LG system. The procedure is the same, so you can go to the BCL and download the Daikin equipment, and that's what I just did. Install those and run the simulation, and then same with LG. There's some LG equipment on the building component library. Although the LG equipment is a number of years older, I believe, about 10 years older. So let's go ahead and take a look at those. We can take a look at the Daikin, this report. So this one comes out to a 132 or 133 kBTU per year, whereas the generic was 124 and the Mitsubishi was 117. And then we can also take a look at the LG equipment. And LG comes out to 123. So, yeah. And there's probably additional things that we can look at. I'm sure the Daikin probably has better performance in some different climates compared to this one. But for this application, it's actually looking like the Mitsubishi performs a little bit better. And we can also look at additional factors like unmet hours, like we had discussed before. But at any rate, that's how you can download this equipment performance from the building component library and run the actual manufacturer's equipment on your simulation. Thank you. Please like and subscribe.